Next, I want to introduce you to equation of a line segment. Let's start with a little sketch. The sketch is going to lead us to the expression. So let's set up a coordinate system. Okay, I'm going to pick up a line in this three-dimensional space, a line segment. So let's have a line right here. This is a line segment, so we'll start with initial point of the segment p sub 0 and the final point on the segment p sub 1. Of course, this line segment is part of a larger of a line L. Okay. So what we're going to do, we're going to construct two position vectors. Let me remind you the difference between a position vector and a free vector. A position vector is a representation of a point in space where the initial point of the vector is the origin 0, 0, 0, and the final, or the tip of the vector, or the final point is the point itself. The final, the end point of the vector is the point itself. So from the origin, the vector that goes to p sub 0 will be defined as r sub 0, and likewise the vector that goes from the origin to p sub 1 will be r sub 1. And what happened is those two vectors represent initial and end points, but any other point on the segment will be r, a generic r. Later on we see it's r of t. Okay? So the direction vector that is corresponding to this will be parallel to the vector that is has the direction of the segment p sub 0, p1. So on the next page, that's what we'll write. Okay, let me split it. You all copy? Anybody need to split? 2 seconds. Okay. So I'll split and then I'll go back to unsplit it. Okay. So the direction vector is the following. For the segment, is V, and we're gonna, if you look at carefully at the sketch, you can see that the segment itself, actually let me change the way I write it. The segment itself is p sub 0 p. Okay, let's say the initial point is p sub 0, the end point is p sub 1. So this is the vector. If you look carefully, if you do vector subtraction, you see that it's r1 minus r0. Okay. Again, look at the sketch, and you can see that this vector is r1 minus r0. Okay. If we add, we need to put r1 at the initial point of r1 connected to the end point of r0 and connect and come up with the opposite diagonal of the parallelogram. Remember, one diagonal on the parallelogram represents the addition and the other diagonal represents the subtraction. In this case, this diagonal of the imaginary parallelogram is the subtraction. So, how this help us? Well, recall that the vector representation or the vector equation of a line is the following. So recall the vector equation of a line, and the first expression we obtain is, we said r And this will be really r as a function of t. Will be the position vector r sub 0 plus a scale of the direction vector v, like so. Okay? But v is the difference of these two vectors, so we can write it as r sub 0 plus t times, t is the scalar, r sub 1 minus r sub 0. And we can factor r sub 0, and the result would be this expression. Let's see, we'll have 1 minus t times r sub 0 plus t times r sub 1. And the restriction on t will be the following. If we go back to the sketch, if t equals 0, then if you look at this expression right there, r equals only r sub 0. So t equals 0 represent the initial point. On the other hand, if t equals 1, then this component is 0 and r equals r sub 1. So t equals 0 corresponds to the initial point of the segment, and t equals 1 corresponds to the end point, to the final point of the segment.